Hi, let us proceed with our discussions. For the design example of an unbraced and slender column, which is subjected to moment in both axes, we have gone through a series of calculation steps, which we have determined the MED for both major and the minor axis based on the equations for the unbraced and slender column. We also found that we need to consider the biaxial bending, and therefore we have identified the minor axis to be more critical than the major axis. Because of that, we will need to work out a new MED, which is on the basis of the minor axis plus the biaxial effects due to the major axis. This has revised the MEDY from 25.8 kN to 42.1 kN. And then based on the MEDY, we have designed and proposed the reinforcement bar to be 6H20. Based on the AS required, since we are dealing with the slender column, the calculations of the second order moment was initiated with the assumptions of Kr equals to 1.0. And then through the calculation steps, we have confirmed that the assumed Kr is valid, and therefore the proposed reinforcement of 6H20 was adequate. Having all these calculation steps completed, there is one more calculation steps we need to do, which is to check the biaxial bending capacity of the column based on the requirements in the Eurocode. To do this, we're going to apply these equations and make sure it is not more than 1.0. Previously, we have discussed how do we find the MED for the major and the minor axis. This was what we have left over since our previous videos. In these videos, we're going to continue with finding the factor A as well as the MED in the major and the minor axis in order to complete this entire process. Without further ado, let us get started. Our next step now is to determine the factor A, which serves as the power of both axes in the process of quantifying the capacity used in the individual axis. In order to determine the A here, we will need to refer to this table. The factor A is governed by a ratio of the axial loads. The ratio represents the axial loads capacity used within the column. We will need to first determine the ratio of NED divided by NRD. Get the value. Whichever value as obtained from the ratio, we will do interpolations in order to work out the factor A. The NED is given, which is 147.36 kN. As for the NRD, it is given in this equation as the summations of the axial capacity of the concrete and the steel. The axial capacity of the concrete is determined by the design strength of the concrete multiplied with cross-sectional area of the concrete, whereas the axial capacity of the steel, it will be the design yield strength of the steel multiplied with the cross-sectional area of the steel. We have the cross-sectional area of the concrete, which is 175 times 300. As for the FCD, it is calculated using this equation. 0.85 times FCK. FCK is 30 Newton per mm square divided by partial factor of safety of concrete, which is 1.5. As for the steel, the AS, it will be the amount non-reinforcement bar provided. Since we are talking about the axial load, all reinforcement bar in the columns shall participate. That gives you a total of 6H20 with the AS provided 1885 mm square. Multiply with FYD, which is 0.87 times FYK. FYK is 500 as given in the question. Substitute the value into the equations. You get axial load resistance of the column equals to 1713 kN. Get the ratio of NED per NRD. NED is given 147.36 divided by 1713 kN. You get 0.086. Refers to the table here. 0.0x is smaller than 0.1. Therefore, we should use A here equals to 1.0 as calculated here. Now that we have the A, we have the MRDZ and MRDY. We need the MEDZ and MEDY. Since this equation deals with the resistance of the moment for the major and the minor axis separately, that means we are referring to their individual moment acting in their axis, which based on our previous calculation steps. We are talking about MED equals to 36.2 and 25.8 kN for the major and the minor axis respectively. Since this equation has already considered the effects of the biaxial bending, we will use the MED as per what we have obtained from the equations for the slender and unbraced column, not the M'ED, and Y that incorporated the effects of the other axis. This clears a doubt which MEDs to be used, since you have several MEDs that you have calculated along the way. The principle is this equations has already considered the biaxial bending effects and the equations by fundamentals looking into their individual capacity used, and as the summations of all, we will see whether the member is satisfactory. Therefore, we shall look into the individual moment acting onto each axis instead of modifying the MED, taken into considerations the influence of the other axis. And then if you observe the MED here, the calculations of the MED is on basis of the two components here. From the calculation step, M min is only 2.95, whereas M2 plus M02 will give you this MED. Now we know that the MED now is governed by the first component here. We have no issue with M2, which is the second order moment, but we have to remove the moment due to the imperfections in the M02, which is the first order moment. You see, when we calculate the M02, as implied in the equation here, we have incorporated the moment due to imperfection. However, when come to the calculations of this equation, the moment due to the imperfections of the non-critical axis will have to be removed. The moment due to imperfections shall only be taken into account on the more critical side, which based on the previous calculations, we know that the minor axis it will be more critical. That means the M for the imperfections will only retain in the minor axis, whereas this M due to imperfections will need to be removed from the major axis, since it is not a critical site. This principle is logical because this additional moment due to imperfections, once it occurs in one axis, the influence it will be minimum. Therefore, you do not need to double count the imperfection moment. Having this concept established, now let us get the M02. The M02 was calculated as 28.4 and 14.9 for the major and minor axis. And we know the imperfections, which was calculated as 1.8 and 1.6 for the major and minor axis respectively. We will keep the imperfections moment in the minor axis. That means the M02 for the minor axis will remain. However, you will need to remove the moment due to the imperfections from M02. By taking this 28.4 minus 1.8, you get 26.6 kilonewton meter. And then go back to the equations to determine the MED, which is M02 plus M2. Now the new M02 after removing the imperfections is this. And then the M02 we have calculated previously after tested with the K, and it ends up to be M02 equals to 7.8 and 10.9 for the major and the minor axis. That gives you the MED to be used in the equation equals to the new M02 plus M2. 26.6 plus 7.8 give you 36.2. 14.9 plus 10.9 give you 25.8. Now that we have all the values for the equations, the MRD for the major and the minor axis are given here. The A is taken as 1.0 and the MED for the major and the minor axis are given here. Substitute into the equations, you found that it is equals to 1.04. This is more than 1.0. It does not meet the requirements to be less than 1.0. That means the provided reinforcement bar is insufficient in this case, even though we go through the calculation steps. Taking into the considerations of the biaxial bending effects due to the non-critical axis, where we provide sufficient reinforcement bar to fulfill the requirement for this M prime EDY, but still it cannot meet the requirements of the Eurocode, having these equations to be less than 1.0. With that, we're going to increase the amount of reinforcement. Initially, we propose the reinforcement bars to be laid in this manner, which give you 6H20 in the minor axis. Since you have 2 reinforcement bar, 4 in the neutral axis of the major axis, only 4H20 will be effective for the major axis. Now that we know that the reinforcement bar is insufficient, we will have to add the reinforcement bar. Probably we'll add another 2 reinforcement bar here. Although it seems like you have a total of 8H20, but when you consider in the minor axis and in the major axis, it will end up to be 6H20 for the minor and 6H20 for the major axis. Why is it so? Let's say we look at the minor axis first. Among the 8H20, 2 steel bars are located at the neutral axis of the minor axis. That gives you only 6 units of reinforcement bar effective in the minor axis. Now if you look at the major axis, 2 bars fall in the neutral axis of the major axis. Out of the total 8 steel bars, only 6 are effective in the major axis. That gives you both the major and the minor axis having 6H20, but in fact you are actually providing a total of 8H20. Based on the amount of reinforcement bar effective in the axis, you get the AS provided. You will use the AS provided, apply into the column design chart in order to work out the new MRD. Based on the D2 per H ratio, which we have calculated previously, and we know that for the major axis we are referring to the D2 per H ratio of 0.15, whereas for the minor axis we are referring to the ratio of 0.25. For the y-axis of the chart, we need to work out the number for the N per BH FCK. No change to the absolute, the dimension remain the same. That means the y-axis N per BH FCK, it will be the same as what we have calculated previously, 0.094. As for the AS FYK per BH FCK, based on the AS provided, multiply FYK, which is 500, divided by BH 175 times 300, and then divided by FCK, which is 30. You get the value of 0.598. Next, you will need to refer to the chart in order to find the value from the x-axis, so that you can work out the moment resistance based on the amount of reinforcement bar provided. Let us first deal with the major axis. Draw a horizontal line at the locations of 0.094 and then refers to the curve of 0.598. This is the one that we're referring, and the scales is given here. 0.598 is very close to 0.6, which is this. Extend from the curve here, and you get the intersection here. Draw a straight line downward. It is about 0.215. That gives you the M per BH square FCK equals to 0.215 for the major axis. You will do the same for the minor axis. Referring to the chart, D2 per H ratio equals to 0.25. Draw a horizontal line at 0.094. And then you need to get 0.598 for the AS FYK per BH FCK, which is this curve. Find the intersections of the point. Draw a straight line down to get the value in the x-axis. That gives you M per BH square FCK equals to 0.17. Having the x-axis value obtained, now you need to get the moment resistance of the section. Multiply this with BH square FCK. Since we are talking about the major axis, the B it will be 175, the H it will be 300. That means 0.215 multiply 175 multiply 300 square and multiply FCK, which is equals to 30. This gives you the MRD equals to 101.6. As for the minor axis, 0.17 multiply B. In the minor axis, the B it will be 300, whereas the H it will be 175 due to the dimensions. We are talking about the minor axis here. The H it will be 175. With that, you have 0.17 times 300 times 175 square times FCK 30. Then you have NRD for the major and the minor axis. Next, we need to determine the ratio A for the equation. Since now you have revised the layout of the reinforcement bar, the total numbers of reinforcement bar has increased from 6H20 to now, which is 8H20. This will have revised the axial capacity of the steel. Because of that, we will need to recalculate the ratio here in order to work out the factor A here. NED we know it is equals to 147.36. As for the axial capacity, the concrete capacity it will be the same, 175 times 300 times FCD. As for the AS here, it will be calculated on the basis of the total at H20, that is 2513 mm square, times FYD. Substitute the equations, you get the axial capacity of 1986 kN. Get NED divided by NRD, it ends out to be 0.074. Refers to the table here, 0.074 is less than 0.1, and therefore you use A equals to 1.0. Now that you have new moment resistance of the column, you also have the A. We're going to apply the MED, Z and the Y that we have calculated previously. After removing the M imperfections from the major axis, your MEDs are given here. Substitute the value, you get 0.91, which is less than 1.0. That means the proposed amount of reinforcement bar are acceptable. Now before you finalize the reinforcement bar for the column, it seems that the column is quite heavily reinforced. Maybe we should do a quick checking in terms of the maximum reinforcement bar limit. Use the AS provided as a result of a total of 8H20 divided by the cross-sectional area of the column, which is 175 times 300. It ends up the amount of reinforcement bar more than 4% of the maximum bar limit. At the lapping regions, the amount of reinforcement bar doubled. Also, it is more than the limits of 8%. That means the proposed reinforcement bar of total 8H20 is not acceptable. Exceeding the maximum amount of reinforcement bar will lead to the members to fail in brittle manner. The solutions for you it will be either to increase the section or to reduce a bit in terms of the amount of reinforcement bar provided. Now, if you choose to redesign the sections, such as enlarging the column, that means you have to redo everything from the start. Designing for the nominal cover, determining the first order moment, minimum moment, second order moment, test the KR, correction factors, check the biaxial bending, work out the MED prime, and then propose the amount of reinforcement bar, check the maximum minimum bar limit, and eventually comes to the biaxial bending checking. So the entire example needs to be repeated again if you are using a new section. Let's say now you would like to try your luck to reduce a bit the amount of reinforcement bar provided in this section here. You make sure you need to reduce the amount of reinforcement to be less than the maximum limit of 4% and 8% of the column's cross-sectional areas. And then you will need to redo this process of checking the biaxial bending in terms of the resistance MRD, also in terms of getting the ratio A, and then to check these equations whether it is less than 1.0. Particularly for this case, reducing the amount of reinforcement is not workable. Reducing the reinforcement bar to be less than the maximum limit will eventually lead to the failure of this equation. This leaves to you the only solutions is to enlarge the column section.